Next speaker is Karen Hannouche. She works in chemistry department of American University at Beirut, Lebanon. She's going to talk about controlled growth of hierarchical zirconium MOF nanocrystals by a reaction diffusion system for water remediation. Go, Karen.
Good morning, everyone. I am Karen Hannouche, a chemistry master's student at the American University of Beirut, Lebanon, and it is my pleasure to be here today presenting my work entitled Controlled Growth of Hierarchical Zirconium MOF Nanocrystals by a Reaction Diffusion System for Water Remediation. Before delving into the specifics of this project, I would like to introduce to you my home for the past 5 years, AUB, the campus of opportunities in which I pursued my bachelor and master's degree and joined Professor Mohammed Ahmedi's research lab. The novel and persistent work of this research group focuses on the fabrication and exploration of highly performant inorganic and hybrid materials for energy and environmental applications. Today, I am excited to guide you through our latest piece of science, and the flow will be as follows. I will first start by giving an overview about metal organic frameworks, moving into the novel synthesis method we're adopting in this work, and its advantages over the physical properties of the zirconium MOF synthesized. Then, as a proof of concept, I will detail how these crystals demonstrate an increase in their adsorptive capacities as compared to their conventional counterparts, to finally take some steps ahead towards possible future works. First, I would like to start by quoting Professor Omar Yaghi, who, speaking of the latest advances in reticular chemistry, said, "When racing toward making materials that benefit society, chemists come back to questions regarding how atoms are linked into molecules and how molecules interact with each other to account for their observation. It has also been our quest, once we acquire this knowledge, to use it for controlling chemical structures and, in many ways, bending them to our will." This systematic control is of significant importance in MOF's chemistry, especially that those frameworks made by linking metal clusters to organic linkers provide a significant degree of versatility within an ordered structure. The highly crystalline, porous, and tunable nature of MOFs makes them potent candidates in a wide variety of chemical, electrical, optical, biological, and environmental applications. While MOF synthesis methods are numerous, many of them require a high energy input at a high environmental cost and/or lack the means to control their outcome. So the synthesis method we're adopting in this work falls under the umbrella of room temperature procedures and occurs via a reaction diffusion process. I explain. Basically, the two building blocks of the MOF are separated into inner and outer solutions. The inner building block is mixed with a gelling agent and poured into a test tube. After gelation, the outer solution containing the second starting material is added to diffuse into the gel matrix. The resulting diffusion flux formed at the liquid-gel interface is proportional to the concentration and leads to the controlled formation of MOF nanocrystals within the gel matrix. The size of these crystals is dictated by both the nucleation and growth rates, whereas smaller crystals are formed near the interface, where the two building blocks are in close proximity, while bigger crystals form down the tube where growth dominates. Our research group has previously succeeded in synthesizing and tuning various MOFs using this procedure, including MOF 199 and zeolitic imidazolate frameworks. So what is this work bringing to the table? It actually reports, for the first time, the synthesis of a zirconium MOF via a reaction diffusion process. And zirconium MOFs, particularly UiO66 systems, are among the widely studied MOFs in literature due to their robustness and multifunctionality that makes them potent candidates for a wide variety of applications. It should be also noted here that the high coordination number around the zirconium 4+ centers in these frameworks makes them prone to structural irregularities, named defects, and these defects can be engineered by the addition of modulators that compete with the organic linker to form more accessible and more performant MOF structures. Delving into the specifics, the diffusion of a zirconium salt into the gelated mixture of dihydroxyterephthalic acid, which is the linker, and acetic acid acting as a modulator, yielded the formation of UiO66OH2 crystals with different physical properties depending on their zone of extraction. So as we go down the tube, bigger crystals are formed, as shown in these SEM images, and as evidenced by the broadness of the main PXRD peaks. The surface area and pore volume of these crystals also parallel the growth trend, and we obtained highly defective structures with the highest defect number of 1.96 for the most refined crystals in zone 3. Next, synthesis recipes and growth trends were established by varying the experimental conditions, starting with the zirconium concentration in the outer solution. While the vertical trends going from zone 1 to zone 3 in each case were conserved, bigger MOF crystals were obtained when the zirconium concentration was changed from 200 to 600 millimolar. This can be attributed to the fact that with a higher diffusing zirconium content, acetic acid acting as a modulator can bind better to the zirconium clusters, thus slowing the nucleation and increasing the growth. Next, the agar gel concentration in solution was varied from 0.5 to 2%, or in other terms, from a thinner to a thicker gel medium. The vertical trends are also conserved here, while a horizontal comparison shows the formation of much smaller crystals within the thicker gel, which upon increase of its concentration in solution has a lower surface area and pore size, so it acts as a scaffold that hinders MOF's growth along the tube. Finally, to study the effect of the type of gelling agent used, we substituted agar with agarose, which has a wider pore size, to lead even much bigger crystals because of the increase in growth. Now that all these established trends are checked, how do these crystals perform compared to their solvothermal counterparts? The zirconium nanocrystals extracted from the 3 zones and their defective solvothermal counterpart, named UiO66OH2SV, were used to absorb methylene blue from water. All MOFs synthesized using this works procedure showed higher absorptive capacities due to their higher defective nature, with the most performant one being in zone 3 with an uptake of around 200 milligram per gram. In order to gain some insights about the absorption mechanism taking place, the pH effect was investigated, and higher methylene blue uptake was obtained at a higher pH. A closer look at the zeta potential of the most performant MOF of zone 3 shows that the MOF surface is positively charged below a pH of 3.5 and negatively charged above it. Since methylene blue is a positively charged dye within the studied range, the electrostatic interactions between the MOF surface and the dye are expected to drive the absorption mechanism. In brief, our green, novel synthesis method of zirconium nanocrystals within a gelated medium constitutes, with all the established recipes and trends, a systematic mean to control the physical properties of highly performant MOFs, bringing us one step closer towards bending materials to our will. Future works are expected to expand the library of zirconium MOFs synthesized using this procedure and delve deeper into their defect-driven applications, mainly catalysis and water remediation. For more details about these findings, you can check our very recent publication in ACS Applied Materials and Interfaces, and this work couldn't have been fruitful without the efforts of the contributors, Patrick Damaset and Dr. Abdelaziz Gouda, and the continuous support and guidance of my great mentor and research advisor, Professor Mohammed Ahmedi. Thank you all for your attention, and I will be happy to answer any questions you might have.
Thank you, Karen. There's time for a couple of questions. Yeah, there.
Thank you, Karen, for the excellent presentation. I was wondering, why do you think that when you synthesize the UIO66 using the reaction diffusion method, why do you get higher concentration of defects compared to the solvothermal method?
Okay, so in comparison with the solvothermal method, our method is much slower. So we're basically achieving a control over the nucleation and growth rate. So we're allowing the modulator, which is acetic acid here, to better compete with the linker, forming more defects in the structure.
So could you control it to actually make it have less defects as well? Depending on, like, you can control the competition between the modulator and the organic linker, right?
Yes. So basically, our aim here was to increase the defects as much as possible since they are crucial for the studied application. But we believe that by tuning the experimental conditions, we can achieve like a controlled trend of defects formation along the tubes.
Okay, thank you so much.
Very nice talk. So I have a couple of questions.
Sure.
So the defect, how did you calculate the defect? And it is the linker defect or it is the node defect?
Okay, so the defects are missing linker defects, and they are calculated using the TGA curves by thermogravimetric analysis. So basically, we use a couple of formulas to compare the theoretical weight to the actual weight of our synthesized MOFs, and we deduce from it the number of missing linkers that are present within our structures.
Not the TGA mass. TGA mass.
Yes, we compare the percentage by mass, the loss of mass when all the linker has been combusted, and we deduce from it the number of defects that we have.
Okay, thank you.
All right, thank you, Karen.